Thank you for the introduction. I am serving as the president of QuEra Computing. My name is Kitagawa. Today I would like to explain to you how practical and fault-tolerant computers are being developed. So our company, QuEra, we are developing and producing a quantum computer that uses cold atom. It started with the technologies by the professors at Harvard University and MIT, and we were able to develop them into technologies. And last year, we had orders worth more than 7 billion Japanese yen, and Google, SoftBank Vision Fund 2, Valor Equity Partners, and others have actually funded us with 35 billion Japanese yen, or a little less than that. Now, so let me explain what this cold atom quantum computing is. So the photo on the left really shows the core part of our quantum computer. Now, within this wired portion, you see this glass. Inside is vacuum, and within the vacuum, rubidium atoms are trapped. And each of the atoms are qubits, serving as a memory of the quantum computers. And laser is used to trap them. And optical tweezer is what the laser is called. And using the laser pulse, we're actually controlling the qubits 0 and 1. And on the right-hand side, you see how that is represented. As you can see here, the beauty or the benefit of the cold atom type is shown here. Many qubits can be laid out in arrays easily, and as the photo shows, many qubits can be operated or worked on in parallel. Therefore, parallelized computation is possible, and therefore efficient computation is possible once we reach such a stage. And so with that kind of a mechanism, we have Akira, which is the first generation quantum computer that we have released and started using since 2022. And so 65 qubits and 130 hours per week is provided, and this is the longest and the largest. And material simulation, optimization problem, machine learning, among others, are the application areas. But quantum reservoir computing, especially in the area of machine learning, is where this Akira has been drawing a lot of attention. Moody's, Amgen, Merck, Deloitte, and others are our partners, and we have together come up with concrete results. And so we believe that there's this power of changing experimental science into computational science. So we believe that we can conduct lattice gauge theory or spin liquid experiments using quantum simulation, and that's been already covered in the scientific journals. And Gemini is the second generation quantum computer. For the first time, it's a commercial neutral atom gate-based quantum computer. And in March, at the end of March this year, finally, we installed this in AIST, and so it's in Japan, and it will start operation this year, and I hope you will get a chance to leverage that. So far, I have been talking about QuEra being actually active in developing and producing the quantum computers. However, originally, the basics, why do we need quantum computers in society? Well, actually, again, experimental science can be converted into a computational science, and there's a potential of dramatic innovation and advancements. When you look back, of course, there have been a lot of discoveries that drove innovation. However, such scientific discoveries were possible by many years of experience. Time and money had to be invested. But what if you could do this by just having simulations in your computers? Then, of course, the tasks can be accelerated. And using classical computers to reproduce the scientific experiments, it would take billions of Japanese yen, costly, because classical computers doing a quantum or physics simulation, it's not good at doing that. Therefore, if we really do this quantum simulation using a quantum computer with the same root, it should be much easier. That was the idea. And therefore, once we scale up this quantum computing, then we can accelerate scientific discoveries. For example, energy efficiencies of solar panels might be improved, or EV battery capacities can be improved. Such major innovation might become possible. Now, within our company, we have been looking at different use cases for research and development. For example, Wellcome Leap program, especially Q4Bio, which uses quantum technology for the discovery of various materials, and inhibitor for muscular dystrophy has been developed, and we have been given awards for that. And therefore, or actually we were awarded up to phase 3. And so drug discovery is progressing thanks to the use of quantum technologies. And of course, many other speakers have already spoken about this. One of the key challenges is for the scientific discoveries, trillions of repeated experiments or trials are needed, and that is because of the high error rate. However, good news is QuEra, jointly researching with Harvard University, came up with this result in 2023. We were able to realize successfully this quantum error correction technology. Error rate can be reduced exponentially. And the video that you're seeing right now is where we used 48 logical qubits in this demonstration. And in 2024, the following year, we have actually realized this magic state distillation.
Now, this is for the first time in the world, we were able to distill the magic state at break-even or more, which is a necessary resource for the QEC. Now, this magic state distillation, maybe you are hearing the word for the first time, so let me just explain about this concept very briefly. This magic state means quantum advantage requiring element. This is requirement in quantum advantage. So any calculation that uses only Clifford gates, it can be efficiently simulated using classic computer. This is actually been proven by Distelman's theorem. So if you have only computation without magic state, it's nothing more than it's nothing different from the classic computer. So that means that if you want to achieve the quantum advantage, this magic state is a necessity. So it is extremely important to reduce the error rate of magic state. And this is something we could actually achieve that for the first time in the world. So based on this result, we were selected to participate in the quantum bench initiatives at DARPA. Now, in this QBI program, the proposal is to propose architecture that can scale toward 2033. So at QuEra, we've been working on QEC with result is thanks to the advantages that QuEra platform provides. There are 4 points that are important. First, the qubit, which is used as memory, is the atom itself, and therefore all the qubits are exactly the same. And also, as you saw in the very beginning, there can be very many qubits in the arrays. So it is possible to prepare like thousands and many more of the physical qubits, and therefore logic qubits are protected. And also it is possible to operate them in parallel. So this is going to be very important when we shift from the physical qubits to logical qubits, because all the logical qubits can be, as a group, can be handled as one. And also the last item is the improvement of the 2-qubit gate, the fidelity of such qubit to be improved. And now the error causes are understood very well, and therefore it can be treated and solved not as a scientific problem, but actually as an engineering problem. So let me give you some details. The point is, in the very beginning, I said, basically, we have the atoms in the vacuum and manipulate them with lasers. So the concept is extremely simple. And because of this very simple system, the result of the theoretical result and the experimental result would match with each other. And as an example, this is the achievement of 99.5% fidelity at Harvard. And the remaining 0.5 error budget is all detailed out here. So by looking at this table, for example, Rydberg state is decaying, and that is the reason why we have array. So with this input, with this information, then you can, for example, decide to reduce the time for Rydberg state. And this becomes a very trivial problem. And to do that, we can enhance the laser power to speed up the calculation. So by having this data, even if the quantum computing seems to be very complex, but simply by changing the component, like enhancing the power of laser, you can solve the problem. So the whole problem can be treated as engineering problem. The system level problem can be broken into component level problems. And also by working with the component vendors, we can enhance and evolve our computing, quantum computing, and also we can actually evolve the quantum computing in parallel. So there's a huge room for improvement through engineering activities. Also, something which excites us a lot is the huge potential for the combination of AI and quantum. There are two aspects. One is AI for quantum, and the other is quantum for AI. Now, regarding AI for quantum, this means how we can use AI to improve and enhance quantum. And at Harvard, we are working with them. And when we analyze and interpret the error corrections, we have to reach the syndrome, and then we have to decode it. And that decoding is really heavy in classic computing. And this decoding can be done by using AI. And if you do that, the quantum computing itself can increase in terms of speed by 10 times or 100 times. So simply put, as you enhance the accuracy or the precision of the classic computing, you can enhance the quantum computing. So this kind of research has attracted a lot of attention. And for example, when NVIDIA decided to establish their quantum research center at Boston, they invited us to be one of the founding members. And we actually started joint research. We actually wrote a paper with them. And the opening of this quantum research center was celebrated. And actually, their CEO and our CEO together talked about the opening of their center in recent event. And the other aspect is quantum for AI. The idea is to use quantum computer to enhance AI. And AlphaFold or be it other things. For the advancement of science, AI is going to be used more and more. But if you use only AI, there's a limit to the evolution because the LLM, the current LLM, if you look at them, let's say that in order to make it into ChatGPT, functional model couldn't do it alone. You had to do the reinforced learning, you had to do tuning, and that means you needed to feed very high quality data to make something like ChatGPT. So the emerging API, if it is used for the quantum simulation, it needs to have very high precision simulation data, and that's where the quantum computer can be used. Another example is AlphaGo. That was not possible to beat a human player if they had only data of the past human players' record. So they always need very high quality, high precision data for simulation, simulated data, and that is where quantum computer can be used. So once you combine the quantum AI, you can benefit by that integration. And so the quantum computer industrialization can happen earlier when we combine that with AI. So based on our activities, now we are providing 3 different services. One is something we delivered to ICE, which is on-premise machine. It is used in governments. And we're going to deliver this for many governments, for many industries, entities. We also provide this capability on cloud as well. And also, I talked about our collaboration with NVIDIA. So we conduct a lot of joint collaborative researches. We are working with world-renowned universities such as Harvard, for example. The last piece is application joint development. This is probably the most important. From the users' companies, when they have a very interesting problems, using the current quantum computing, we can work with the user companies to cover not only the solution itself, but the hardware aspect as well. And so if you are interested in solving a specific problem, please talk to us. We can jointly develop the whole system. Maybe you have a problem, but you don't know how to solve it with the current quantum computing. If we explore, maybe we can find a good solution. So through this presentation here, this is the message I wanted to deliver to you. The message is that we're shifting from physical qubit time to logical qubit era, and how to be successful in logical qubit era is something that we are trying to achieve. Thank you.
Thank you. There are a few questions that have arrived, so I'd like to spend the next few minutes to cover questions.
Minutes to address some of the questions you've been sending. So the first one is in English. Has any development or collaboration research on cooling atom quantum computers taken place in Japan? ということで、中性原子の関連。
So it's about joint research on a neutral atom. Is it progressing in Japan? Is the question? Yes. Already a few. I think the question is focused on the neutral atom. Yes, there are some potential or proposals for joint research. Nano-T, for example. Interconnect is being made by this company, and they're very much, they have a lot of insight into neutral atom, and there's a proposal for joint research, and we're acting towards that. Now in Japan, with AIST, of course, we have introduced our product, and therefore, with that, we have established a Japanese base here, an office here in Japan. We want to grow that, and we want to also address the supply chain, jointly researching with parts suppliers, for example, or joint research with companies that are developing the latest technologies. In other words, in order to develop the ecosystem for quantum computing in Japan, I'd like to make contribution. Another question.
Rubidium is the best choice, or is there any other atoms you're considering? Well, at least now we believe that rubidium is the most well understood atom. But of course, if good quantum computer is possible, we're open to any other options. So it's not like we welcome if you have any idea to suggest any other atoms. We welcome. And in 2026, 100 logical qubit bit, that is a roadmap. How much have you made a progress? Successfully, we are moving along very well. We are developing different machines, and also we are developing the future designs to achieve this goal. Thank you. And of course, QBI program at DARPA, this is also moving along, and we are getting a lot of support from them. And also the last question.
Higher the laser power, the higher the computational speed. Is that correct? Yes. There might have been some misunderstanding or misleading. In that context, higher the laser power, the Liudberg drive speed will be higher, and therefore 2-qubit gate operation will be faster. The computation itself has other factors involved as well. For example, the speed at which the atoms are being moved around. So the overall speed of the quantum computing itself will not be defined there, but we're talking about 2-qubit gate speed being higher. Thank you. Please give a big round of applause once again.